Yeah, thank you. Sorry again for the technical complications in the last minutes. So yeah, thanks a lot. First of all, thanks a lot to all the organizers for the invitation to be here. Let me preface by saying that by training I'm a mathematician, and I just kind of relatively recently started working in AI. So my point of view and my vision and the description of this talk is going to be very, very different from the ones that we've seen before. So I'm going to be specifically talking about PDE, partial differential equations, and I'm going to be talking about sort of our long-term view, and I'll be more specific about what I mean, and how AI and PDE in this concrete context are going to be interacting, or how we plan for them to be interacting. So the truth is, when I first got invited, I saw the title of the talk, Mathematics for and by LLMs, and I told the organizers, look, I'm flattered, but I don't do LLMs. And then they said, don't worry, talk about it. But in the end, I am going to talk about some LLMs. So at least for a few minutes. So last week, AlphaEvolve was announced. I am part of the group and has been working on AlphaEvolve in the context of mathematics. This is section 3.2 in the white paper that was released. I am not allowed to answer a lot of questions about this, but let me know if you want to know something else. So this is joint work with Terry Tao on the math side, and then on the Google DeepMind side, Alex Davis, Bogdan Georgiev, Ray Zhang, and Adam Wagner. Okay, so the paradigm here, or at least the way, or one way in which AlphaEvolve works, as opposed to, let's say, other LLMs, is that the interaction is not so much through natural language, and instead is done via coding. This is not a new idea. This is not something that has been figured out right now. So, for example, FunSearch, which was a previous product from DeepMind, but also many others, have discovered that actually the interaction through code results in getting more accurate or better outputs or better results, whatever you call it. So now the paradigm is, instead of saying, well, dear ChatGPT, can you solve this problem? The question is going to be more, dear ChatGPT, can you write me a program that solves this problem? Okay, so it turns out that somehow that way of acting works better, and the way or one way that AlphaEvolve works is by evolving. Well, first it was a piece of code. Now it's a full repository containing hundreds or thousands of lines of code, and sort of effectively, little by little, fine-tuning and getting better and better programs. There is a score function that essentially, which is provided by the user, that effectively says, well, this program is good, this program is not so good, and then based on that kind of ranking, it evolves and it leads to a program that is satisfactory, whatever that means. So we designed a benchmark of about 50 problems, open problems, real mathematics problems, of varying degrees of difficulty from extremely different fields. Here's a small sample of them. There are more. And what we found was that in 75% of the cases, roughly, AlphaEvolve was able to essentially say what the best humanly known result was, which is probably the optimal for those kind of questions. In 5%, it was worse. And in about 20%, it was better. Okay, so it improved some problems in many different areas, by some margin. Okay, so we were quite happy with this kind of numbers. We are moving into more problems and harder problems, and I'm not claiming that this is like superhuman. Probably any human with enough training and enough time can beat these numbers. But what I'm claiming is that this is super fast, because every one of them took less than 2-3 days. It didn't require previous knowledge, like previous deep knowledge. I mean, it requires to know some form of mathematics, but not really a whole lot of the field or the setup or anything like extremely deep about that. So that's I think the upshot of this method. Not so much the depth, but the breadth. Okay, so what I claim is that this can give a fairly good result for a wide class of problems in a very reasonable time. Okay, so this is sort of the end of my advertisement. We're back to PDE, and as I said, well, the title of this talk is Mathematics for Large Language Models. But in fact, I'm going to talk about something else, which is small models for mathematics. Okay, so and this is joint work with Buckmaster, Calabora, Lai, Leger, and Wang when not quoted, and when quoted with whoever I quote. So my claim is that in the last 3-4 minutes, I showed a bunch of examples, like very like a big breadth. Now this is going to be focusing about depth. So we are only going to be focusing in one problem or in one class of problems, and see that you may not need a large language model to progress there. So in fact, a really tiny model, especially compared to what now large means, can do some improvement, and I'll show a few examples. Okay, so spoiler. This is the deep problem that we are trying to go towards. Okay, so we want to solve the Clay Millennium Prize. This is the existence of global solutions or breakdown of regularity of solutions to the Navier-Stokes equations in 3D, incompressible, set up in the whole space R3. Okay, and as along the way, as an intermediate project, there is the 250-year-old problem concerning 3D Euler, so no dissipation here. There is no term in red, which is also open in the case of 3D. Okay, so we want to say something about this question. Does there exist a smooth initial data, finite energy, no cheating, that leads to a finite time singularity? So we believe the answer is yes, and the hope is that we can construct an example of such an initial data that leads to finite time blowup. Okay, so that's where we want to go. I'm not going to be announcing this, but sort of I will talk about some progress that we have been doing over the last months, over the last year or so. So this is pretty hot right now. In the last 5 years or so, there have been many results relaxing this hypothesis. So there are results, for example, taking non-smooth, but not very non-smooth, so not ridiculously non-smooth, but failing by a little, initial data that develop a finite time singularity. These are 3 examples. And then there are other examples that what they play with is the domain. So these equations are set either on the T3 or R3. But if you look at them in the interior of a cylinder, then Chen and Hao, building on previous work by Luo and Hao, have managed to prove the existence of singularity formation on the boundary of the cylinder. So this configuration is forbidden if we want to go to the full space using a computer-assisted proof. Okay, so this is essentially what is going on in this field for the last 5 years, and it is somewhat expected that somebody is going to prove this in the next few years. Okay, because the field is getting a lot of momentum, and we hope that with the introduction of AI, things can be boosted even more. Okay, so this is the dream. proving finite time blow-up without boundary and using a combination of machine learning, a computer-assisted proof, and let's say more traditional classical analysis. Okay, so something that I will be discussing for some part of the talk is something called a self-similar solution. So a self-similar solution is the following. So let's look at the panel first on the left. The panel is a numerical simulation of the one-dimensional Burger's equation. And you see that in finite time, a shock is forming at the origin. So the function stays bounded. The gradient blows up in finite time. Okay, so finite time singularity formation. But what is interesting here is the red rectangle, because if we zoom in at the right rate and rescale, this is what we see. So we see that the yellow curve stays put. The blue curve corresponds to the rescale version of the blue curve that we were seeing before. Okay, so this is an instance of a self-similar or asymptotically self-similar solution. And this is the object that we are going to be looking for. Instead of trying to look for something that becomes infinite or its derivatives become infinite in finite time, we're going to be looking for the object on the right. Okay, so mathematically, we're going to be looking for solutions of our PDE that are of this form for a given capital F that we don't know, and for given alpha and beta that we don't know either. And some relations between alpha and beta are going to be dictated by the equation, but we will have some degree of freedom. Okay, the upshot of this ansatz is that even though little f is singular at a certain time, capital F is smooth, and it's going to be smooth all the way up until the blow-up time. So for a computer, finding f is impossible, finding little f, but finding big F may be possible in principle, assuming that there is such a solution, which is maybe a big if, but we'll see. Okay, so the point is that these solutions are important, and we can use them as building blocks of a construction of finite time singularities. So in other words, if we were to find any f that solves any capital F that solves this the equation for this form, for this shape, then by design we don't need to worry about proving blow up, because by design the little f is going to be blowing up. Okay, so now our goal has shifted from finding the little f into finding the big F. Okay, and in order to do so, if you remember the previous video, there was some kind of notion of convergence to the self-similar solution as we approach the blow-up time. So essentially, this is the sort of mechanism that we are trying to find. Think of the right panel before. So every point here in this ball represents a solution in self-similar coordinates, and what we want to prove essentially is that there is some sort of ball in a way that our solutions don't escape. And if we do that, then we win. If we do that, then we are guaranteed that when we unfold the coordinates and when we go to xt, any point in this ball will correspond to a solution that will blow up in finite time. So now the goal has been first transform into finding capital F, and second, relax even more into finding a neighborhood such that the solutions are not going to escape. I'm cheating a little bit, but let me cheat for now. And the plan is to say, well, I'm going to relax it even more, and I'm going to try to find something that satisfies approximately the equation, and then sort of look at a neighborhood of that approximate solution. And then if I can prove that there exists a neighborhood around the approximate solution such that I don't escape, then I'm done. But the point is that I cannot do this anywhere. I need to do this in a neighborhood of something that is very close to the solution. This is also where machine learning is going to come into play. Okay, so this was linear stability. If everything is small, then nonlinear effects are small, other errors are small, And then if we can understand the linear problem, then the nonlinear problem would be a small perturbation of it, and we shouldn't care too much about it. Okay, so that's the plan into how to prove finite time singularities for both Euler and Navier-Stokes. Okay, this is maybe a longer version of it, but it's essentially what I said. So step 1, find an approximate self-similar solution. Step 2 and 3, prove linear stability, and these are some suggestions about how can one prove such linear stability. And finally, 5, upgrade linear to nonlinear stability. Okay, step 4 is important because step 4 essentially tells us that we can go from Euler to Navier-Stokes and treat the viscous term, treat the Laplacian as exponentially small, as an exponentially small forcing, assuming some condition in the self-similar scaling exponent. Meaning, if the red box goes to 0, shrinks fast enough, then dissipation doesn't have any time to happen. So the scale in which the dissipation acts is much slower than the case in which the singularity form. And I will give more quantitative estimates as to where does this come into play. But the bottom line is, if we can manage to prove singularity formation for Euler, then perhaps we can treat Navier-Stokes perturbatively from Euler itself. Okay, so this is the plan, this is the roadmap, and this is the kind of approach that we have been taking and working on for the last years. Okay, so note that I didn't say anything about the PDE. This, assuming that there is such a solution, in principle, and assuming that all the numerology is good enough, should work for any PDE. And the plan is to use machine learning, and we will be using pins for the first part, which is right now the bottleneck, and then use a computer-assisted proof for the middle ones. And step 5 is done by hand with plenty of effort, but it can be done. Okay, so my plan for today is to talk mostly about step 1, variations of step 1 for different problems that are not Euler, but are trying to get there. Okay, so I won't say too much about how to turn the approximation of the finite time singularity into an actual mathematical proof, and I will be focusing more into what is the role of AI and how we can take advantage of AI and what one can do in this kind of business. Okay, so this is a generic model. In this audience, this begs no introduction, but essentially what I want to highlight here is that the neural network that we're going to take is extremely small, 6 by 30 for the 2D problems, 3 by 20 for the 1D problems. So this is, in terms of parameters, is somewhere in the order of several thousands, so extremely, extremely small in this context. And then we're going to minimize the weights and the biases, over the weights and the biases, the equation residue from the PDE, the boundary conditions, and perhaps some additional terms coming from symmetries, and maybe some special terms depending on the equation. Okay, but in general, what we're going to try is to minimize over the W's and the V's that appear in every arrow from every neuron, to minimize the equation residue, perhaps the derivatives of the equation residue, and so on. Okay, so note that this is, well, highly nonlinear, because we have compositions of nonlinear function and affine function. Okay, but yeah, so small, really small networks. Okay, let's go back again to Burgers, and let's see what are the dangers of trying to use this approach for certain PDE. I mean, Burgers is nice because Burgers, we can calculate everything, and everything is explicit. So this is 1D Burgers, no dissipation. And if we go to self-similar coordinates, remember the alpha and the beta that I mentioned before, this is our ansatz for our solution. We need to find capital U. In this case, we only have 1 degree of freedom and denoted by lambda. So we need to find a pair u comma lambda of this equation 1, taking out the time derivative. Okay, we need to find a fixed point of equation 1, and in order to do that, we need to find the approximate profile, capital U, and the approximate scaling, namely the rate in which the red square shrinks as part of the problem. Okay. So we can solve implicitly that because it becomes an ODE. If we write y of u instead of u of y, then the equation becomes an ODE, and we can solve it. So that's nice. Remember, we are looking for smooth solutions u. So u needs to be smooth, and this poses a constraint in the values of lambda. So lambda, in order for the solution to be smooth, needs to take a hierarchy of solutions. In this case, we can compute them explicitly. So lambda needs to be of the form 1 over an even integer. But any other value of lambda will lead to a solution, but it's not a solution that we want. It's going to be a non-smooth solution, and we don't want those. So generically, for any generic lambda, the solution is not smooth and therefore bad. There is a sequence of lambdas, lambda n, that give rise to smooth profiles. And maybe what is important here, and I will comment on this later, is that if as lambda n as n grows, then the solutions become more and more unstable. So if n is 0, we have the ground state. This is typically stable. This is the one that if we don't do anything, the solver will converge to. But as we go to lambda 1 u1, lambda 2 u2, and so on, then the profiles become more and more unstable. Convergence is more and more difficult. And in general, any solver struggles. Okay, so this is something important here. And what we want to do, or what we have learned, is to use machine learning methods to discover lambda n un for moderate values of n, not just the first one. Usually, the first one is a lot of work, and going past 1, it's typically impossible, unless you know this is maybe a very easy case where you can do things. But in general, computing unstable solutions is a very hard task, no matter the method. Okay, and even more so in this case, where it is unclear that such solutions exist. There is no guarantee that we have any solution to our PDE of the following form. Okay, so that's the task. And for burgers, this is what happens, but I claim that generically, this is also what is going to happen for many other PDE. Okay, so now let me talk about other 1D models. So the first 1D model that I'm going to comment is something called the CCF model. This is coming from the work of Cordova-Fontelos. The equation itself doesn't matter. The point is that now there are two scalars, u and omega, that are related via some non-local operator. So this is now not an ODE anymore, or a system of ODEs anymore. And essentially, everybody talks to everybody in space. Okay? So why am I bringing this up? I'm bringing this up because we're going to use this model as a sort of mental model to think about Euler and Navier-Stokes. Because this model has viscosity. And depending on the viscosity, if the viscosity is small, then there is a finite time blow up. And if the viscosity is big, then there are global solutions, because then the linear part dominates, and this becomes like a heat equation. So the point is that, and there is still a gap in between these two values of the viscosity. So let's look here. This is the important piece. This term here, coming from the viscosity, when written in self-similar variables, is going to be exponential. Now, the sign of the exponential is going to be crucial, because if the sign is negative, then this is great. This is an exponentially small term. It won't really affect at all the self-similar solution converging to somewhere. And if it is positive, then it will just go away, and this is terrible. So what it really determines whether this has a chance to be treated perturbatively is this condition here coming from the exponent inside the exponential. So alpha times 1 plus lambda being smaller than 1 is good because this becomes negative and we have an exponentially small term. If this is bigger than 1, then we are in trouble. Okay, so if we were to do something in the open range between 1/2 and 1, we need lambda to be smaller than 1. If you think about burgers, the lambdas go down as you go into more and more unstable regimes. So one expects that if one has like such a condition for Navier-Stokes, which one has, one will need to go to the very unstable solutions of 3D Euler. So it is important and interesting to understand how to go there. Okay, so it is likely that one will need to construct highly unstable solutions to Euler in order to prove blow up for Navier-Stokes in this way. Okay, so this is what we found. We did find relatively easily the first stable solution, meaning the blue curve on the panels. This is again using pins. But we also found, which was a lot harder, the first unstable. So the first unstable corresponds to lambda roughly 0.6. This is more or less the profile that we found, and we had to struggle a lot. Back then, these are relatively old results, and we found that it was unstable. It had one. The dimension of the unstable manifold was 1, and the proof of their existence leads to blow up for the other open problem for alpha smaller than roughly 3/5. Okay, so we are happy because we are sort of understanding the mechanism for being able to put viscosity into the problem. Okay, and we can test. We can also use machine learning to find eigenvalues. The left and the center panel are the trivial eigenvalues coming from the symmetries of the problem. We can get them with 10 to the minus 5 accuracy. And the rightmost one corresponds to some other thing that we cannot tell physically what does it mean, but it just means that there is a non-trivial eigenvalue somewhere with a positive real part, and therefore it is unstable. There is an unstable manifold and has dimension 1. Okay, so I won't get into the details today, but the point is that we can prove that around our approximate profile, omega bar, lambda bar, we can find a codimension 1 smooth neighborhood such that it leads to finite time blow up for the equation that I showed before with some dissipation exponent smaller than 3/5. Okay, if we were thinking about what does it mean for this from in the context of Euler and Navier-Stokes, we would have to be able to go all the way up to alpha equals 1. Okay, so but nonetheless, we expect that by going to higher and higher unstable modes, we could still be able to do it. Okay, let me talk about a slightly different problem. This is another 1D equation coming from 2D Euler. But here, the vorticity, which is the curl of the velocity, is concentrated in a free boundary. Okay, so the vorticity, the curl of U, is 1 here, 0 outside. And one can write the evolution PDE as this is the normal velocity, and this is some sort of singular integral operator acting on the normal component of the curve. So we are parameterizing the free boundary here, and everything is determined if we know how this free boundary evolves with time. Again, this is a 1D model that is challenging because of the non-local singular integral happening that has a logarithmic singularity in the kernel. So we're going to look for global solutions that correspond to some rigid rotation with some angular velocity omega. Before us, this is a very old paper, 1978. People had done numerical continuation from the disk, which is a steady solution, and found these objects that each correspond to a different value of omega, and that their behavior is to rotate with that angular velocity omega. And a few years later, if one keeps going through the branch, what one finds numerically is the following. So this corresponds to these blobs that rotate, but as you go through the branch, as you move in omega, there is some sort of limiting configuration that is conjectured to have a 90-degree corner, no matter what amount of symmetry you work with. Okay, so all of these angles are conjectured to be 90 degrees corners. Okay, and this is still an open problem from 1986. Okay, so this is now the object that we're going to be interested in. Okay, so the plan is to find some examples of these kind of potato shapes using machine learning. The claim is that even if there is a singularity or that there is some bad point, machine learning methods can handle this. Now, how do the equations look like? They're going to be nasty. They're going to look in the following way. So there's going to be this parameter omega, then some local terms, and then some horrible non-local terms corresponding to the singular integrals that I described before with a logarithmic kernel. Okay, the exact form doesn't really matter. The point is that there is this free parameter, which is not free because omega needs to be distinguished. And again, if you think about the self-similar problem, it's a similar setup where most of the values of omega don't work. They don't give us the object that we want. And there is some sort of hierarchy of solutions that leads to good solutions in the form of what we're looking for. And the equation itself has some singular integral behavior. Okay, so even using traditional methods, this is not easy. There are a few papers, our own unpublished work. This is joint work with Maria Prat-Colomer, who is my graduate student now at Brown. And we're going to use machine learning. So the hard part, or one of the hard parts, is the corner, how to work with the corner, and decide, for example, whether this constraint on the corner can be incorporated into the design of the space or as part of the loss, as an additional term to penalize and to see if it converges better. And there is also this thing about omega, that there is only one value of omega that works, or a discrete set of values of omega that works, so we need to handle that. Okay, so this is how we were able to handle this. We did some highly accurate numerical integration, and we also, okay, there you go. Okay, and we also started through a warm start from a qualitatively similar solution, and we use Adam plus LBFGS for the training. And here you can see the errors going down and the omega moving around through the training, and we can get to relatively accurate solutions by using this kind of techniques. Okay, so this is more or less a summary of what we did. We tried several sampling strategies, and these are sort of the important metrics are here on the left. The smaller, the better. This is the value of omega that agrees with the literature to 6 digits. Nobody in this field reports errors. If you think about releasing code, it's impossible. So essentially, we don't have anything to compare with other than our own implementation of the classical method, which is the row corresponding to baseline, and we can beat it by several orders of magnitude, and this should be enough to effectively prove the existence of these objects in the case where they have twofold symmetry. Okay, so these are the comparisons of the errors using the log of the errors using the baseline solution, which is a classical spectral method with some twists. And these are, depending on the sampling strategies, and the description of the functions, how the errors look like in one case and in another. And we see plenty of improvement also in the computation time as well, which I didn't mention, but the machine learning code is way faster than, let's say, our implementation of the classical method. Okay, so we are happy about that. And what we can do is to go even beyond and be able to prove it. This is Maria, myself, and another student of mine, Gerard Castro, who we have managed to, all together, to prove the existence of these objects using a computer-assisted proof and using some asymptotic analysis, weighted spaces, classical analysis, etc., that I won't talk about it today. Okay, all of this was 1D. Now I'm going to be moving into the 2D direction. Okay? Yes.
I think I missed how was the neural network used.
Oh, the neural network is to use used to find this all of these candidates have been used to all of these candidates have been found by the neural network.
But how exactly? How do you encode the equation to the neural network?
Oh, the equation is encoded through the loss. The object function that you minimize is the loss, the discretized loss, sometimes via maybe gradients or Hessians of the loss. So you minimize overall your parameters in the network that are like the W's and the B's from the affine functions. You use those as your parameters, and what you're training to is minimizing the loss, and in that case is the PDE itself, plus maybe the boundary conditions or symmetry conditions, etc.
So you transform the PDE into a loss minimizing program.
Correct.
Okay.
Yes. Yes, but we don't need to use a ridiculous amount of parameters. So that's also nice. Somehow this works. And if we were to, I mean, we've tried with like massive networks, no improvement, took a lot longer, and it just didn't improve. We don't know why, but even trying with like bigger networks, it didn't make a difference.
Okay, but so can you do this for any PDE, or is it specific about
any is a very strong word. We've tried I don't know, half a dozen models, and we have been for these sort of things we have been quite successful. What I think I'm most proud of is not solving the PDE, but discovering the solutions. In the sense that if I come here today and I tell you, look, this is my approximate solution, I'm sure you can go back home and find it yourself, no matter how. I mean, with a little bit of care. But the discovery part is very important, because none of these solutions are guaranteed to exist. So you don't really know where to look for. And this, by other methods, nobody had been able to find them before. So what I find the most appealing feature, besides the compression and the low time complexity and so on, is the discovery. So this is the part that I like the most about this, and this is essentially the difference between giving up and not giving up.
Is your search technique essentially to just start with random networks and just keep trying it?
At the very beginning, yes. You see quickly, there are like sort of two phases. So you get very rapid improvement, then lots of stagnation, and then you have to do something about it, which I'll comment, and then you can improve even better. So typically, these sort of solutions stagnate around a precision level of 10 to the minus 6, 10 to the minus 8, depends on the problem. And the next question, which I will address, is how to go from 10 to the minus 6 to 10 to the minus 15. And that requires a new twist. Okay, but so yes, you see very rapid improvement, and then very slow or no improvement.
So you start from a random initial condition, it will typically turn into nothing, or
if you do things more or less okay, it will give you something.
It will usually give you this 10 to the minus 6.
Yeah, exactly. Okay. Maybe not at first, but you don't need that much of help, let's say. So yeah, the canonical initialization is random. The sampling is random, and yeah, many of the features are random themselves.
It's not like a needle in the haystack. There's a lot.
There are phases where it becomes a needle in the haystack, and then okay, you learn tricks, and then with those tricks, then nothing is a needle until you encounter like the next. So for example, what do I mean by that? Finding the stable solution was easy, but then we were blocked as to how to find the first unstable for a long time until we came up with a new trick. So, and then it was easy, but then we were blocked finding the second one, and so on. So we are slowly unblocking the possibilities of this method by banging our heads against the wall and devising better methods that seem to, or better heuristics that seem to work better. But from, let's say, one solution to the next one, there is a problem that we don't know how to solve until we solve it. Okay, more questions, comments? Okay, so this is 2D Boussinesque. This is important because it's a very close cousin of 3D Euler in the presence of a boundary, both in the presence of a boundary. So here we have a system. Everything lives in 2D in the upper half plane. Theta is a scalar, U is a vector, and P is a scalar. And again, same game, go to self-similar, try to solve the self-similar PDE. Here, there are even more tricks because the pressure is a non-local function, so we don't like non-local things too much. So we're going to get rid of it. And we work with vorticity formulation that leads to a local PDE. So now our equations are local. We don't need to invert the Laplacian across many scales, which is typically something very difficult for classical methods. And we impose some degrees of symmetry and some vanishing conditions at infinity, and this is what we found. Okay, so these are relatively old results. This is sort of the time when we started working on this kind of problems, and we were getting results of fields of the size 10 or 1, and errors of size 10 to the minus 4, 10 to the minus 5, and so on. And our exponent matched with some hints from the previous literature that were available by the time that we started doing this. Now this was, I mean, now it feels easy because this solution is stable. This solution is the very first one in the hierarchy of solutions for this 2D Boussinesque. And then we struggled. This is kind of coming back to Mike's question. We were struggling a lot to say anything. I mean, we didn't know if there was the next solution, the first unstable, and so on. So we spent a lot of time struggling with this. And again, keeping in mind that our end goal is to get to Euler. And for Euler, there is very little chance to succeed unless we go through the unstable solutions. Okay, so we have been working with a lot of people from DeepMind trying to get this to work. Okay, so we are planning to. I mean, we are finishing a paper, and we will release a paper very soon, probably by the end of this month or maybe early next month. Okay, so this is how the panorama looked like when we started working. We had our own paper, and there were some previous results for the 1D model. Okay, so now this is how it looks like today. Okay, so we have managed to really improve in the context of unstable solutions, finding more in this 1D model and a lot more, and even 6 more for certain PDE. This is 2D, this is 2D. So now we understand a bit better the heuristics and the methods to make things work and to be able to have relatively confident solutions that are even unstable and have unstable manifolds of dimension, well, 4, 5, 6, something like that, which are not too big but not too small either. Okay, so some more comments about how we have been able to get there. We now can do things with ultra high accuracy, meaning typical machine learning methods will take you there if you're lucky, but not beyond. Okay, so really there is this cycle where, and this has happened so many times, that we got some output from the machine learning, and then it suggested a structure. No guarantee whatsoever. But then we thought hard, and then we did some math and some, I don't know, clever changes of variables or analysis. And then we realized, like, oh, this is correct. This is really happening. So let's encode it into the model. And then we put it back into the model. And then once we put that back into the model, the convergence was more stable. We could get further. We could get better. And after a while, there was yet another structure discovered, and we sort of sat down, did the math, figured out that was happening again, baked it into the model, and kept going. Okay, so this process has happened a few times, and it has led to really lots of improvements into how to set up the system, what the heuristics may be, and so on. So, for example, one thing that right now is really important is to incorporate the asymptotic analysis at several points into the model, and this really leads to more stable convergence and faster. We have also used some asymptotic relations of lambda, and even doing some kind of extrapolation once we got enough solutions. If we got like 3 or 4, then the 5th one we could do a little bit of extrapolation, and that essentially took us quite close to the next one. We also changed and improved on the method, on the optimizer. This is following the ideas of James Martens, who is at Google DeepMind and an expert in this second order optimization methods. And so we used a sort of beefed up version of Gauss-Newton, more details in the upcoming paper, that is order 2, very slow per iteration, but extremely fast convergence. So in practice, every iteration takes a long time, but we need to do very, very few iterations. Bad news, as always, plateaus at 10 to the minus 8, but then we can fix this using a multi-stage or multi-scale approach developed by Wang and Lai that go all the way from 10 to the minus 8 to 10 to the minus 15. Okay, so this is how we can get quite accurate solutions using machine learning methods, which is new, at least in this community, to very high precision.
What is capital H?
It's an approximation to the Hessian. This is where the trick is lying. So it's not quite the Hessian. This is why there is this approximate here, but it's an approximation of the Hessian. Okay, so just to wrap up, ML methods are powerful and can lead to new discoveries in PDE. So I'm advocating for ML methods towards discovery. And it can find instances of solutions that have certain properties, and it can even work under bad conditions. LLMs are starting to be working quite well generically for a very broad class of problems, but for specific and typically much harder problems, maybe we don't need to go to large models. Maybe small models can do better. Maybe we can learn something more from the small models. And this is what I think is universally correct, is that we know extremely little, and there are lots of things to explore yet. So this is quite exciting these days. And let me stop here. Thank you.
I'm curious about the multi-scale method to go from 10⁻⁸ to 10⁻15.
Think of a wavelet. That's the mental picture. That so you want to work in higher frequencies and in smaller scale, like smaller amplitude scales. So if you think about a setup that is reminiscent of a wavelet, this is the kind of thing that we're doing, connecting several networks at different scales. Yes.
And so this self-similarity trick that you change the variables and make it self-similar, is that specific for the Navier-Stokes equation? Or
No, this is relatively standard to prove singularities for many PDE.
Okay. And also, you mentioned alpha evolve.
Yes.
That was not related at all to this work, right? Or
No.
was it?
No, Alpha Evolve is a different project than both are done in collaboration with DeepMind, but both the internal and the external people on both teams are different. Yeah, Alpha Evolve is more about breadth, and Navier-Stokes is more about depth. Yes.
Yeah, this is probably far over my head altogether, but I was wondering, you kept referring to a hierarchy that imposes the non-stable solutions. Would you mind trying to explain to me what that hierarchy, where that comes from, and does it depend on, even your initial parameter sets or the directionality you're taking?
Right. Okay. Let me go back. Probably the best way to look at this is to look at burgers, where everything is explicit. Yes. So this is burgers. This is the solution to burgers equation in subsimilar variables in an implicit way. And there is the constraint that we haven't used at this stage, that the solution needs to be smooth. Okay. So if I impose that, then this constrains lambda to take one of these values. These are the possibilities for lambda. And then in order to lead to a smooth self-similar solution, lambda can only take these values. Okay, so you have a discrete set of possible index, let's say index by I or by n of possible solutions, lambda n, un. Now what happens in this hierarchy is that u0 is the ground state. u0 is the most stable solution. And
My question, yeah, I might be just too stupid to get it.
No.
To me, it's not evident why that imposes a hierarchy.
Okay, maybe what's the definition of a hierarchy?
Well, to my understanding, it would be some directionality and
it is not clear.
formalism that.
What I mean by the hierarchy is first the index of this, which you can argue like it's just a way of counting, but the hierarchy comes from the dimension of the unstable manifold. So the first one is the one for which the dimension of the unstable manifold will be the smallest, then the next one is going to be higher, then the next one even higher, then the next one even higher, and so on. For burgers, you can do that calculation as well by hand, and you obtain that this lambda n, the dimension of the unstable manifold of un, is actually n. So you have this hierarchy of more and more excited states and more bigger and bigger unstable manifolds. Whether this is true for other equations, we don't know until we prove it. No, but it is conceivable, and we've seen other instances, like compressible Euler, for example, is another equation that satisfies this kind of thing. Okay, so we have seen instances that doesn't necessarily have to hold for every single PDE in the world, but in the cases that we have been working with, up to the point where we have discovered enough solutions, this is satisfied.
Thank you.
Yes.
So in the case in which you reach 10 to minus 15,
Yes.
I mean, if you do different optimizations, starting from different initial conditions, do you converge to the same one, same network, or different networks? I mean, are you interpolating with, do you have a manifold of interpolating functions, or it's just one?
There is only one solution.
There is only one solution.
Yes, there is only one exact solution. Then depending on if you use a different network, your space of functions is different.
No, but I mean the networks that you get at the end that parameterize your function.
And they are off by numbers that are of that order of magnitude, like 10 to the minus 14, 10 to the minus 14. We don't get the exact floating point number depending on the initialization and so on. We get things that are within each other on like 10 to the minus 14, 10 to the minus 13.
But if you look at the weights, for example.
They are within each other.
Okay.
From the point of view of the function, they are very close. So, okay, I didn't show it, but usually when we plot these kind of diagrams, we have like error bars accounting for the random initialization. Not, of course, whenever it converges, there are obviously instances where the network just fails. I'm not claiming that this is 100% safe and it will always converge and it will always take you there.